Hello and welcome to lesson 2 of unit 3, Implicit Differentiation. Today we're going to be talking about differentiating implicitly defined functions and solving for dy dx. So first, let's talk about what makes what makes a relation an implicit relation versus an explicit relation. So an implicitly defined relation is one where the relationship between x and y is not explicitly defined, nor can one be easily determined without removing some elements of the relationship. So for example, a couple explicitly defined relations that you may know is the top half of a circle, right? Y is equal to the square root of 64 minus x squared. That's the top half of a circle with a radius of 8, and it is a function. And this is the equation of a line. This is a linear function. I could solve for y to get an explicit definition of y in terms of x, and none of the line is taken away. It's still the exact same graph, even after I solve for y. Some implicitly defined relations, y squared plus x squared is equal to 64. So from geometry, you might recognize this as the whole circle with radius 8. I can't solve this for y without removing some elements of the graph. And we'll see that in an example in a moment. Another implicitly defined relation would be something like sine of x is equal to sine of y. There's absolutely no way for me to solve for y and maintain the type of relationship that's defined in this equation. I would encourage you to pull Desmos up and graph sine x equals sine y. It's kind of an interesting looking function. Relation. It's definitely not a function. And check it out. So writing an explicit relation. So for the example that we just saw of y squared plus x squared is equal to 64 in the implicitly defined functions, relations, I really should change that to relations. We could solve this relation for y. However, when we do, I get a plus or minus. So I have to now choose the top or the bottom. I don't have the entire circle. So solving for y in this case eliminates some aspect that was originally defined in the implicit relationship. So this is an implicitly defined function, an implicitly defined relation that I cannot solve for y without removing elements of the graph. So to differentiate an implicit function, we have to consider that the variable that you are not differentiating with respect to has some explicit definition in terms of the differentiating variable. It exists, but it's just not shown. Therefore, the chain rule applies to every variable that you're not differentiating with respect to. So for example, let's take that very same circle equation, y squared plus x squared equals 64, and let's solve for dy dx. So what we will do is differentiate the entire equation. I'm going to differentiate the left and the right side. And what happens is every term ends up being differentiated independently. So starting from the right, the derivative with respect to x of 64 is 0, because it's just a constant. The derivative of x squared with respect to x is just an implementation of the power rule, 2x. And then the derivative of y squared with respect to x, this is the first time that we see this implicit differentiation thing. So I'm thinking about y as being some function of x. And so this really is a chain rule. It's the function y of x to the power of 2. So I have this outer function of something squared, and the inner function is y. So when I differentiate, a chain rule happens. So I still get the 2 times y, that's the implementation of the power rule, but that dy dx pops out as it's the derivative of the inside function, which is y. Now I just have to use algebra to solve for dy dx. So dy dx is equal to negative x over y. And a lot of these problems where we're implicitly differentiating, our answer is going to end up having both x's and y's. It's not always the case, but a lot of the times it does. Okay, let's look at another example. Find dy dx for the following relation. So we will start by differentiating the entire function. We're ultimately differentiating each term individually with respect to x. So the derivative of the constant is 0. We have an instance of differentiating x squared with respect to x, so that's just 2x. But then every one of the terms that has a y in it, because I'm differentiating with respect to x, I get a dy dx that pops out as a consequence of the chain rule. Okay, and each one of those terms that has a y, I have an inner function y of x that is raised to a power, and that outer power is the outer function. So take just the y cubed example. The derivative with using the power rule is 3y squared times the derivative of the inside, which is y, and the derivative of y with respect to x is just dy dx. So we represent that as dy dx. Now it's just a matter of using some algebra to isolate that dy dx. All right, there we go. And from this point on, you'll notice that, writing dy dx, it can get tiresome. So a lot of times, instead of writing dy dx, we'll just write y prime. So it's sort of a shorthand for when we're differentiating implicitly, to just write y prime as the dy dx that pops out as a result of the chain rule. All right, so let's take a look at, I believe this is the last example. Find the slope of the line tangent to the curve that at the point 3, 1. Okay, so start by differentiating both sides of the equation with respect to x. On the left side, we do have, not only is there a y, so there's going to be some form of implicit differentiation that's happening, but there's also a chain rule that's happening. If I choose not to expand that binomial of x squared plus y squared quantity squared, I can treat that as a chain rule. The outer function being something squared, and the inner function being x squared plus y squared. So the derivative of the outer function, I multiply by the old exponent of 2, decrease the exponent by 1, so now it's just down to 1. And then that what's in purple there, that's me differentiating the inside of what was being squared. Okay? Now, I haven't done the differentiation yet. I'm just preparing to do it. And then on the right side, I'm just making a note here that x times y, that gets treated as a product rule. It's x times y. So there's a product there. So the product rule has to come into play. Okay. So with the purple part, differentiating x squared just becomes 2x. Differentiating y squared becomes 2y, and out pops that y prime, the consequence of the chain rule and implicit differentiation, differentiating with respect to a different variable. On the right side, my product rule, first times the derivative of the second, the first being x, the second being y. So first x, the derivative of y is y prime, plus y, the second, times the derivative of the first, which, since the first is x, the derivative of x with respect to x is just 1. The rest here is just a lot of algebra. I'm expanding things, I'm distributing things, trying not to make things so messy that it becomes difficult to isolate, but ultimately my goal here is to get y prime on one side of the equation, or every term that has y prime in it on one side of the equation, so that I can then factor out y prime and then ultimately divide by what's left. So there's y prime. This is a function that represents the slope of the line tangent to the curve at any point x, y. Well, I was asked to find the slope of the line tangent to the curve at a specific point. So now we just need to plug 3, 1 in for x and y and compute. So 13 over 9. So the slope of the line tangent to the curve at 3, 1 is 13 over 9. Okay. So in summary, when differentiating a relation, anytime we are differentiating a variable with respect to a different variable, the chain rule comes into play, and I have to multiply by the derivative or prime of whatever that original variable was. Okay. Thanks for watching, and I will see you in the next video.